Hello, good morning dear students. Welcome back to my Electrochemistry class. Today I am going to discuss about one of the application of conductometry measurement. That we have discussed the various applications of the conductometric measurements, okay, or the application of electrolytic conductance. And this is one of the method, this is one of the application that I am going to discuss today, that is the determination of ionic product of water. So the application of conductometric measurement. Conductometry, determination of ionic product Kw of water. Okay, so we want to determine, so wish to determine the Kw of water by carrying out a conductometric experiment, and how it is possible, that is the principle going to discuss. So it is very important, the examination viewpoint, it may be asked as a part of the essay. As all of you know, a sample of water has a tendency to dissociate to a very small extent it is own ion, that is H plus and OH minus ion, as H2 reversibly gives H plus OH minus ion. The extent of dissociation is so small that in a sample of water, out of 5,000 parts of water molecule, only 1 part of H2O is undergoing dissociation, so that the solution is extremely dilute with respect to the concentration of H plus and OH minus ion. So this fact you have to follow. So you have to understand the important fact is that with respect to H plus and OH minus ion, the aqueous solution is extremely dilute, because the water has a very small amount of dissociation, a feeble dissociation. Out of 500 parts of water molecule, only 1 part undergo dissociation to H plus and OH minus ion, and this H plus and OH minus ion then comes in equilibrium with the undissociated part of the water molecule, which is the major amount. Because it is assumed that the amount of H2O is practically remain constant even after the dissociation. Therefore, the ionic product of water Kw is equal to the concentration of H plus into the concentration of OH minus divided by the concentration H2O, which is practically a constant. So since it is a constant, it is assumed that it is not undergoing changing, so you can take it as Kw of water as H plus into OH minus ion. And as all you know, at 25 degrees Celsius, the value of Kw is equal to 1.02 into 10 to the power of minus 14. 10 to the power of minus 14 mole square. Okay. This mole square liter raised to minus 6. You don't go for this units. It is simply a number, because it's an equilibrium constant. It is just like an equilibrium constant. That constant in this case of water is called a ionic product of water, Kw. Okay. That is, actually this comes like this, but this denominator H2O, the part, the concentration of dissociated water molecule is practically constant, because out of 5,000 parts, this is only 1 part undergo dissociation, so it is 4999. So it is practically is constant. So you have to no need to write that, because it is unchanged, it is remain as such. So we have Kw is equal to concentration of H plus into concentration of OH minus. So it is called the product of the ions of the water molecule, and it is called ionic product of water. Now how it is going to be discussed conductometrically. Now we wish to determine the value of Kw as like this by measurement of conductometric measurement. So it is possible. Okay. I already mentioned the concentration of H plus ion and the concentration of the OH minus is extremely small, that the solution is dilute and infinite dilute with respect to the H plus and OH minus ion. The solution of water molecule is considered as at stage of infinite dilution with respect to the concentration of H plus and OH minus ion. Okay. In a sample of water, it is found that the molar ionic conductivity of H plus ion at infinite dilution, lambda m of H plus ion at infinite dilution is found to be conductometrically is found to be 349.8 ohm raised to minus 1 centimeter square. The molar ionic conductivity, or molar ionic conductance, okay, that's conductance of H plus ion is lambda 0 m H plus is 349.8 ohm raised to minus 1 centimeter square, and that of ionic conductance, molar ionic conductance at infinite dilution, okay, this infinite dilution always, the molar ionic conductance of OH minus ion is, that is also can be considered as at infinite dilution stage. OH minus ion by conductometric measurement is found to be 198.5 ohm raised to minus 1 centimeter square. So these are two values that is obtained by the conductometric measurement. The H plus, the ionic molar ionic conductivity of H plus ion is 348.9 and that of OH minus ion is 198.5. Okay. Therefore, the molar conductivity of H2 can be taken as molar conductivity or the sample of H2 at infinite dilution, so it is considered as infinite stage of infinite dilution, is taken as equal to, go to Coleridge's law, that is equal to lambda 0 m H plus into plus lambda 0 m OH minus, that is taken as 349.8 plus 198.5, that answer is found to be 548.3 ohm raised to ohm inverse centimeter raised to minus 2. Okay, ohm inverse centimeter square. So this is a value of the molar conductivity of a sample of water obtained by conductometric measurement, which is taken as that of the stage of infinite dilution. So lambda 0 m H2 is like this. Then the measured specific conductivity, of water is the measured specific conductivity of water. Specific conductance or conductivity of water, as also by conductometric measurement, is found to be 5 point of pure sample of water, pure water is equal to 5.54 into 10 raised to minus 8 ohm inverse centimeter raised to minus 1. Okay, so we have three values, conductometric values obtained by conductometric measurement with respect to water. For water we have three conductometric values or three parameters. That is one of the ionic conductance of H plus ion at infinite dilution 349.8 and that of OH minus ion ionic conductance 198.5. Therefore, the molar conductance of water's molecule is, when adding these two according to Coleridge's law, 548.3 ohm inverse centimeter square. and the experimental measurement of the measured specific conductance of conductivity of pure water is 5.54 Newton raised to minus 8 or inverse centimeter raised to minus 1. As you know that, assuming the water is at infinite stage of dilution because it is only slightly ionized. It is slightly ionized, we can take it as lambda m 0 of H2O is equal to, okay, K product of specific conductivity into V, where K is the specific conductivity. K is the specific conductivity. That is specific conductivity into volume, where, it's very important, where V is the volume of the solution containing 1 mole per cc of H plus ion and OH minus ion each, where V is the volume of water in centimeter cube containing 1 mole of H plus ion and 1 mole of OH minus ion. So you have to stress this thing, this point, where V is called the molar volume. So lambda 0 mH2O is now, as already you know by definition, is the product of specific conductivity and volume, where V is volume of water in centimeter cube that contain 1 mole of H plus and 1 mole of OH minus, and this is because it is the molar volume. Okay. So this statement is very important, where V is the volume of water containing in centimeter cube containing 1 mole each of H plus and OH minus ion. Therefore, we have to find out that volume. Therefore, we know this one. Lambda 0 H2 is known to us. Kappa is also known to us. Therefore, the volume V is equal to lambda 0 m H2O divided by kappa. Specific conductivity. Lambda 0 m divided by specific conductivity. Okay, that is equal to. Now go for the substitution. You know the value. The volume of the solution Cc containing 1 mole of H plus and 1 mole of OH minus ion of water sample is V is equal to 5. Now we again 5 lambda 0 m, that is 548.3 divided by 5.54 into 10 raised to minus 8, so much centimeter cube. Okay, so much cc. So this is the value. So this is, so the volume of the water containing 1 mole of H plus ion and 1 mole of OH minus ion is 548.3 divided by 5.54 Newton to the power of minus 8 centimeter cube. Okay. So alternatively we have to find this calculation. So just now we are going for, therefore alternatively, that is, this is the volume of water containing 1 mole of H plus ion and 1 mole of OH minus. Therefore, the number of moles present in, okay, that is number of moles of H plus and OH minus ion present in V centimeter cube is 1 mole and H plus and 1 mole of OH minus ion. Therefore, the number of moles of, so I can write in, therefore, that is, the number of moles of H plus ion and OH minus ion present in V cc's, V centimeter cube of pure water is equal to 1. Okay. Number of mole 1 each. 1 mole each. Therefore, the number of moles of H plus and OH minus ion present in 1 cc, 1 centimeter cube of water is equal to what is so you know that the volume of water containing 1 mole of H plus ion and 1 mole of OH minus ion is 548 divided by 3 divided by 5.54 into 10 to minus 8. Okay, this is a volume. The number of moles of H plus ion present in B centimeter cube of water is 1 mole each. Okay, 1 mole of each of present in. Therefore, we have to find out the number of moles of H plus ion that is present in B mole. 1 mole of 1 cc of the water is 1 divided by this much. Is equal to 1 divided by B, that is 1 divided by 548.3 divided by 5.54 into 10 raised to minus 8, that is equal to 5.54 into 10 raised to minus 8 divided by 548.3. 548.3, that is equal to, that is our value. This is the number of moles of H plus ion and OH minus ion present in 1 centimeter cube of water is this. 1 cc of water is this. Therefore, our definition, the number of moles of H plus ion and OH minus ion present in 1000 cc, 1 liter, present in 1 liter or 1000 centimeter cube, 1 liter or 1000 centimeter cube of water is equal to that into 1000. Okay, that is equal to 5.54. Oh, this answer found to be 5.5, that is 1.01 into 10 the power of 8. 10 the power of, that is minus 8. Okay, the number of H plus ion or OH minus ion present in 1 cc of water molecule is 1 divided by this value, 1 by this value, plus 5.5. This one numerical simplification we get as 1.01 into 10 the power of minus 10. Okay, actually this answer now obtained is, okay, that is numerically substitute this, that is equal to 0.010 into 10 the power of minus 8, that is equal to 1.01 into 10 raised to minus 10. This is the number. Okay, so much moles. So we have to find out. So next is, therefore, the number of moles of H plus and OH minus ion present in 1000 cc, 1000 centimeter cube or 1 liter of H2O is equal to 1.01 into 10 the power of minus 10 into 1000. That is equal to 1.01 into 10 the power of, okay, 10 the power of minus 7. This into this 10 raised to minus 10 into 10 cube, this raised to minus 7 moles. That is, so a sample of water molecule contain 1.01 to 10 raised to minus 7 moles of H plus ion and 1.07 mole to 10 raised to minus 7 moles of OH minus 7. So that is each. So number of moles of H plus ion and OH minus ion present in thousands here what is 1.01 into 10 raised to minus 7 moles each of H plus and OH. Therefore Kw, as you know that Kw, that means H plus ion is equal to 1.01 into 10 raised to minus 7 moles. OH minus ion is equal to 1.01 into 10 raised to minus 7 moles. Therefore Kw is equal to H plus into OH minus. Now it is equal to 1.01 into 10 raised to minus 7 into 1.01 into 10 raised to minus 7. That is equal to 1.02. 1.02. Okay. 1.02 into 1.02 into 10 to the power of 1.02 something, not 1, okay, 1.01 into 10 to the power of minus 14. It's 14 mole square, okay, centimeter, okay, dm raised to 6. So you don't go for this unit, dm raised to minus 6. So the Kw water now found to be 1.01 into 10 raised to minus 14 moles per mole square liter raised to minus 6 or dm raised to minus 6 liter square. Okay, you can read them d raised to minus 6 or liter square. So you no need to. So this is the Kw water. So this is the method for the determination of Kw of the water. So the basic is that you have to measure the molar ionic conductivity of H plus ion, the molar ionic conductivity of OH minus ion, then specific conductivity of pure sample of water. Then sum of the molar ionic conductivity of H plus and OH minus ion gives the molar ionic conductivity of water at infinite dilution because H plus ion and OH minus concentration is extremely small. So that is on adding we get the molar conductivity of water. And specific conductivity is also known by measurement for pure sample of water, and then molar conductivity is equal to kappa into V. Then you find out the volume, where V is the volume of the solution in centimeter cube, containing 1 mole of H plus ion and 1 mole of OH minus ion. That is important. Where V is the volume of water. So volume of water, sample of water containing 1 mole each of H plus ion and 1 mole each of OH minus ion. So evidently, you have to find out the number of moles present in 1 cc of water, V cc water containing so much. So V is equal to lambda m divided by kappa. You get a volume in centimeter cube that contains 1 mole each of. Okay. Therefore, the number of moles of H plus ion that is present in 1 cc of water is that 1 divided by that. So you get another value. Then the number of H plus ion or OH minus ion present in 1 liter of water, that's 1000 cc. That you get this value each. So ionic product is this into this. You get 1.02 into 10 raised to minus 14. That's it. So okay, I hope that this value, all these measurements are carried out at 25 degrees Celsius. So conduct to metric